Hello, Vital Sign. Today we're going to look at the fascinating subject of domination polynomial roots. If you haven't already, I suggest you watch my earlier videos on the domination polynomial. Based on a property I covered in a previous video, which is that there are no constant terms in a domination polynomial for a graph with at least one vertex, then for graphs with at least one vertex, 0 will be a root of the domination polynomial. However, what can we say about the other roots a domination polynomial might have? Specifically, what can we say about their location in the complex plane? This is where it gets interesting. To begin, we'll derive the following alternate formula for computing a domination polynomial, from which we can get a lot of information about the roots of domination polynomials. What exactly is going on in this sum, and why does it produce our domination polynomial for arbitrary graph G? First of all, we're summing over all possible subsets of the graph's vertex set. Or in other words, we're summing over the elements of the power set of the set of vertices in our graph. For example, if our graph G was this graph, then these would be the sets we would sum over. For each subset S, we raise -1 to the power of the size of that subset, and then multiply that by z plus 1 to the power of the number of vertices n minus the size of the closed neighborhood of our subset, where we define the closed neighborhood of a subset to be the union of the closed neighborhoods of each vertex in that subset. We then sum these values that we just computed for each possible subset and simplify. So that's what's going on in the sum. But why does this compute the domination polynomial of a graph? Well, remember that it doesn't matter what order we sum the values in. So to really see where this formula comes from, let's impose an order on how we sum over the power set of vertices. It will be the same order I displayed for you in this example. For any graph G with n vertices, we'll start at the empty subset, then sum the values for all of the subsets of size 1, then for all of the subsets of size 2, and so on, up until the single subset of size n. Now that we have this order, do you see a pattern? There seems to be an inclusion-exclusion going on here, with the flipping signs for subsets of consecutive sizes. On the next slide, you'll see the general pattern of what we've set up. I'd like to point out two things in this general pattern. The first term here is the generating function for the number of subsets of any size of our vertex set with n vertices. And each z plus 1 to the n minus the size of the closed neighborhood of subset S is the generating function for the number of sets that are disjoint with and have no neighbors in subset S. This is because since the size of the closed neighborhood of S is the number of vertices that S is adjacent to or includes, there are only n minus the size of the closed neighborhood of S remaining vertices in our graph to choose from to create sets that are disjoint with and have no neighbors in S. This is a very important fact because each set whose closed neighborhood is disjoint with S is not a dominating set in the graph. It's also clear that if a set A is not dominating in a graph, then there has to be some subset of vertices S in that graph that is disjoint with A's closed neighborhood. Coming back to our formula, what we want to find is the domination polynomial, which is the generating function for the number of dominating sets of any size in a graph. The coefficients in the first term of our formula clearly overcount the dominating sets of each size because they're counting all subsets in the graph. To account for this, note that by our earlier fact, for each non-dominating set A, there must exist a vertex that is not in A and that is not a neighbor to any vertex in A. Also, when a subset S contains a single vertex V, this term here is the generating function for the number of subsets of vertices in G that do not contain V and whose neighborhood does not contain V. Essentially, it's counting the number of sets that are what we will call non-dominating with respect to vertex V, which just means that the closed neighborhood of those sets does not contain vertex V. That is what this subtraction comes from in our formula. We are letting S range between each vertex in our graph, summing up the generating functions for the number of sets that are non-dominating with respect to each vertex in our graph, giving us a generating function for the sum of the number of subsets of each size that are non-dominating with respect to each vertex. The coefficients of this generating function count every non-dominating set in the graph at least once, because every non-dominating set is non-dominating with respect to at least one vertex. However, there could and probably will be some overlap, as a set can be non-dominating with respect to more than one vertex, and so would be counted multiple times. So now we have to include the counts of subsets of each size that are non-dominating with respect to each pair of vertices, which is given by this sum. And we continue with this inclusion and exclusion until we're left with our domination polynomial, whose coefficients on the k degree term are the number of dominating sets in our graph of size k. Now that we've derived the formula, which we'll refer to as our first formula, we can introduce a new theorem about the roots of domination polynomials. Our theorem is, if G is a graph with n vertices, and if we let delta of G represent the minimum degree of any vertex in G, then all roots of the domination polynomial of G lie within or on the circle in the complex plane with the underlined radius centered at -1, 0. To prove this theorem, let's go back to our first formula and substitute a variable y for z plus 1. What we obtain is a formula in y for the domination polynomial of G and Z. Note that the intuition for this is that y is the distance from the point -1, 0 to z in the complex plane. What we want to show is that when y is greater than the radius in our theorem, the formula for computing the domination polynomial does not evaluate to 0. Continuing, let's define a function f of y to be equal to this sum, which is almost the same as our formula for the domination polynomial, except that it excludes the summand corresponding to the empty subset and multiplies each summand by -1. What this allows us to do is rewrite the domination polynomial as y to the n minus f of y. As y to the n is just the term associated with the empty subset that we excluded from our first formula to form f of y, and f of y is just the negative of the rest of the sum in our first formula. So by subtracting it from y to the n, we have just an alternate representation of our first formula. Next, note that if S is a non-empty subset, then the size of the neighborhood of S is at least delta of G plus 1. This is because even if our subset S contains only a single vertex, its closed neighborhood must still contain at least delta of G neighbors as well as the vertex itself, as we define delta of G to be the fewest number of neighbors for any vertex in the graph. This gives us a size for our closed neighborhood of at least delta of G plus 1. And if a subset contains more than a single vertex, then its closed neighborhood is at least as large as that of any of its member vertices, meaning it's still at least as large as delta of G plus 1. Next, let's turn to the formula for f of y and assume for a moment that the absolute value of y is greater than 1. Then since we deal only with non-empty S in f of y, we have this inequality, because if S is a non-empty subset, then the size of the neighborhood of S is greater than or equal to delta of G plus 1. Now, since we have 2 to the n minus 1 summands to add up in f of y, the absolute value of f of y is at most 2 to the n minus 1 times the absolute value of y to the power of n minus delta of g plus 1. Now hold on to this result for a moment, and let's transfer it to our previous slide. As we mentioned before, this result holds when the absolute value of y is greater than 1. Next, let's see what happens if the absolute value of y is greater than 2 to the n minus 1 to the power of 1 over delta of g plus 1, which is just another way of writing the radius in our theorem. The first thing to notice is that the absolute value of y is also greater than 1 in this case, as we're generally considering graphs with n greater than or equal to 1 vertices. That means the result we just obtained, which is in the line above, is applicable in this case as well. Also, it's not hard to derive that the absolute value of y to the power of n must be greater than 2 to the power of n minus 1 times the absolute value of y to the power of n minus delta of g plus 1. You only have to use the inequality in our initial assumption for this case. I encourage you to show our newest inequality is true. Putting it all together into one string of inequalities, we can see that the absolute value of y to the power of n minus the absolute value of f of y is positive, meaning that the absolute value of the difference between y to the n and f of y is also positive, implying that d of gz is non-zero when y, the distance of z from the point -1, 0 in the complex plane, is greater than the radius stated in our theorem. This proves our theorem that the zeros of any domination polynomial must lie within or along that circle centered at -1, 0 in the complex plane. Isn't that a cool theorem? Moving on to our next topic, let's examine the integer roots of domination polynomials. First, we'll need to use a theorem that the number of dominating sets in a graph is odd. We won't prove that theorem in this video, but I'll leave a link in the description with 3 proofs of that fact. Secondly, note that if an integer b is congruent to c mod 2, then the domination polynomial of a graph evaluated at b is congruent to the domination polynomial of that graph evaluated at c mod 2. Now suppose b is an odd number. Then b is congruent to 1 mod 2. So the domination polynomial of any graph g evaluated at b is congruent to the domination polynomial of g evaluated at 1 mod 2. And since the domination polynomial evaluated at 1 is simply the number of dominating sets in the graph, which is odd by our previous theorem, then the domination polynomial evaluated at an odd number b is still odd, meaning it is non-zero. This proves that all integer roots of domination polynomials are even. Now let's hold on to this result and recall our earlier result about the location of the roots of domination polynomials. We can use it to make an interesting statement. Let G be a graph with n vertices whose minimum degree is at least 2n over 3 minus 1. Any integer root of d of gz will either be -2 or 0. The proof is the following. We know that delta of g is at least 2n over 3 minus 1. By our theorem 1 about the location of domination polynomial roots, we also know that if an integer w is a root of g's domination polynomial, then the absolute value of w plus 1, which is really just its distance from -1 on the real line, since w is an integer, must be less than or equal to 2 to the n minus 1 to the power of 1 over delta of g plus 1. In this case, delta of g is at least 2n over 3 minus 1, meaning that delta of g plus 1 is at least 2n over 3. Then if a number w is a root of the domination polynomial of g, we have this inequality. Note that this is less than 2 to the n to the power of 3 over 2n, which is the same as the square root of 8. Therefore, if an integer w is a root of d of gz, the absolute value of w plus 1, which is the distance between w and the point -1 on the real line, is less than the square root of 8. That means that w could be -3, -2, -1, 0, or 1. And since we know that there are no odd roots of domination polynomials, we can rule out -3, -1, and 1, revealing that any integer root of g must be either -2 or 0. This result essentially says if a graph has enough edges, then its domination polynomial's integer roots are either -2 or 0. Now, it's also been conjectured that this result holds for all graphs, but that's still an open question. Moving on, let's look at just two more properties of the roots of domination polynomials. First, let G be a connected graph with n greater than or equal to 2 vertices. If the domination polynomial of G has all real roots, then the minimum degree, delta of G, is 1. To prove this, note that for k greater than or equal to n minus delta of G, the number of dominating sets with k vertices is exactly the number of subsets with k vertices. That is, no subset with greater than n minus delta of G vertices is non-dominating. This is because, for a subset S to be non-dominating, there must exist some vertex in the graph whose closed neighborhood is disjoint with S. Yet since the smallest degree a vertex can have is delta of G, meaning the smallest closed neighborhood possible in our graph has size at least delta of G plus 1, if we take a subset of more than n minus delta of G plus 1 vertices, we have to include either V itself or one of its neighbors. Regardless, non-dominating sets of size greater than or equal to n minus delta of G cannot exist. So the number of k dominating sets where k is greater than or equal to n minus delta of G is just n choose k. Next, this fact allows us to derive yet another formula for computing the domination polynomial as the difference of the generating function for the number of subsets of all sizes in our graph with some function h of z of degree n minus delta of G plus 1, which we define to be the generating function for the number of non-dominating sets of sizes 1 through n minus delta of G plus 1. Finally, to prove our theorem, let's assume that all roots of d of gz are real. Then by Rolle's theorem, we can say that all the roots of the n minus delta of G plus 1th derivative of d of gz are also real. We can rewrite this derivative like this using repeated applications of the power rule for differentiation on each term. The constant a is simply the coefficient of the n minus delta of G plus 1th degree term in h of z, which was reduced to a constant through repeated differentiation. Also note that the rest of the terms in h of z turn to 0 through repeated differentiation, and the first term in our right side of the equation is just the repeated derivative of z plus 1 to the n. Now, since all roots of this derivative are real, we know that the exponent, delta of G plus 1, must be less than or equal to 2. And because we assume G to be a connected graph, delta of G must equal 1. Our proof is complete if G is a connected graph with at least 2 vertices, and if its domination polynomial has all real roots, then G's minimum degree is 1. The final property we're going to look at is this. Let G be a connected graph with n greater than or equal to 2 vertices, and remember that delta of G is the minimum degree of any vertex in G. Then the domination polynomial of G has at least delta of G minus 1 non-real roots. To prove this, suppose that d of gz has r real roots. It follows that d of gz has n minus r real roots, as d of gz is a polynomial with degree n. Next, using Rolle's theorem, the n minus delta of g plus 1th derivative of d of gz must have at least r minus n minus delta of g plus 1 real roots. Using the representation of domination polynomials from our previous result, we can rewrite this derivative. However, by our previous result, we also know that this derivative has at most 2 real roots, allowing us to set up the inequality below. Moving the n's and r's to one side, we find that n minus r is greater than or equal to delta of g minus 1. And remember that n minus r is the number of non-real roots for d of gz, so our proof is complete. That was a lot of theorems that we covered. Here they are, all in one place. That's it for this video. In future videos, we'll take a look at optimal graphs for domination polynomials. Thanks for watching. Please subscribe, like, share, and comment if you liked the video. Have a great day.